Welcome everyone. Today we are going to explore a fascinating topic in mathematics known as the Gauss Circle Problem. This is a story about a circle, a grid, and an ongoing mathematical mystery that remains unfinished to this day. Let's start with the basics. The Gauss Circle Problem originates in the mathematical field of number theory. The core question is wonderfully simple. If you draw a circle centered at the origin with a radius of r, how many integer lattice points fall inside or exactly on the boundary of that circle? Mathematically, we are looking for the number of coordinates m and n that satisfy the inequality. M squared plus n squared is less than or equal to r squared. To understand this, we first need to define what a lattice point is. An integer lattice is the set of all points in Euclidean space whose coordinates are integers. In n dimensions, it is denoted by z sub n. In our two-dimensional scenario, the integer lattice is the familiar square grid of points with integer coordinates, such as 0, 0, 1, negative 1, and negative 1, 0. A point like 1.5, 2 is a fractional point and is not counted. So the real question boils down to finding out how many pairs of integers fit inside our circle. How do we count them? This number is approximated by the area of the circle, which is b times r squared. This approximation works because on average, each unit square within that area contains one lattice point. Therefore, the actual count of lattice points inside the circle is close to its area. The real problem is to accurately bound the error term, describing how the number of points differs from the area. The first progress on a solution was made by Carl Friedrich Gauss, hence its name. Let's look at those numbers. If we expect that n of r equals b times r squared plus e of r is an error term that has a relatively small absolute value. As you can see in the data, for a radius of 4, the exact count is 49, while the area is about 50.27, giving an error of negative 1.27. For a radius of 12, the exact count is 441 compared to an area of 452.39, giving an error of negative 11.39. The challenge here is to determine a suitable upper bound for the absolute value of E of r. While bounding the error is hard, the value of n of r can be given by several series. In terms of a sum involving the flow function, it can be expressed exactly as n of r equals 1 plus 4 times the sum from I equals 0 to infinity of the floor of r squared divided by 4i plus 1 minus the floor of r squared divided by 4i plus 3. A natural generalization of this is the primitive circle problem. Here we count only the primitive lattice points, which means we calculate the number of coprime integer solutions where m squared plus n squared is less than or equal to r squared, and the greatest common divisor of em and n equals 1. In other words, only lattice points whose coordinates are coprime are counted, and this number is denoted by v of r. Returning to our original error term, what happens when we scale this up? As the radius r increases, the n of r stays very close to pi times r squared, but the error oscillates and is difficult to predict. For instance, at a radius of 20, the error is positive 0.36, but at a radius of 30, it swings to negative 6.43. To conclude, the Gaussian circle problem asks for the exact number of integer lattice points inside a circle of radius r. The area provides an excellent approximation, but a small error term always remains. Understanding the behavior of this error term is one of the oldest and most challenging unsolved problems in analytic number theory. Despite over 2 centuries of research since Gauss, the optimal bound for the error term is still unknown. This problem beautifully illustrates how a simple geometric question can lead to profound mathematical discoveries. As the saying goes, it is simple to state, difficult to solve, and beautiful to explore. Thank you.